Hi, Jasmina. Hi, Jasmina. Jasmina.
Hello, how are you?
I'm doing fine. How are you understanding this stuff? I really need to know. Kind of
For the most part, I think I'm getting it.
Okay. Really and truly, Jasmina, the problems are not simple. It's just wading through all of the information and being able to put it in the right spot. Okay.
Yeah, there's a lot.
I understand that. And probably it would do you good to go and look at the videos on the online outline. Okay. Have you tried any of the problems? I'm not talking about the My Courses. I'm talking about the extra homework type things.
Not yet. I haven't gotten a chance to because I have a bio exam today, so I've been focusing on studying for that.
Crap happens, okay? I mean, we all have to adjust. And by the way, I don't know whether it's going to be a single person or whether anybody else is going to be joining us at this point. But if nobody joins us, that's fine because we can get more done.
Yep.
Okay. I'll wait a few more seconds or so. I'm trying to find out where I need to be. Okay. Cassidy's in. Good. Okay. Simple problem like this, Jasmina. Simple problem like this. Are you understanding where you're going to have to put what? Cassidy, are you there?
Yeah, I'm here.
Okay, same question addressed to you. This is a simple problem. Do you understand what goes where?
I get it, yeah.
Okay.
Yes, I do.
All right. I don't want to repeat myself because we are a little bit behind here. Okay. Now, when I involve something else, the other important thing is to realize, and I'm not taking these out. Yeah, I'm taking these out of context. What you really have to understand is the Q of the surroundings is negative the Q of your system. And basically, you are choosing your system. It's hard to determine the temperature change of something like a hot piece of metal that's cooling down in water. It's hard to do that. You can't stick a thermometer through the metal. So you have to do that by indirect means. You put it in something that you can measure, like water. So basically, you just have to understand that whatever is happening to your system, the exact opposite sign. The number is going to be the same for your surroundings, but the sign is going to be the exact opposite. And it kind of makes sense because the metal is losing heat when it gets put in the water. The water is gaining heat. Okay? Are we good with these two things so far?
Yeah.
Gabe? Gabe, we good with this? Gabe?
Professor, yeah, so far.
Okay. Now, I really don't want to belabor this too much, but all right. Now, when we involved the calorimeter reading, you also have to understand that the calorimeter is part of the surroundings. So whatever is happening in your system is going to be equal to what happens in the surrounding water and the calorimeter, because the water and the calorimeter are both absorbing energy. So the third equation we have to realize is that when we're dealing with a calorimeter that's absorbing heat, the energy absorbed is equal to some constant times the change in temperature. And the change in temperature is going to be the same as the change in temperature of the water. So if I'm dealing with a question like this, then negative the Q of the metal is going to be equal to the Q of the water plus the Q of the calorimeter. And I can set it up as one big long problem, just like this, where I plug things in here. The 52.1 grams for the metal. S is what I believe we're trying to solve for. Change the temperature of the metal. The final temperature was 28.3. Initial temperature was 79.8. Subtract those two out. Then we got the weight of the water. Specific heat of the water is a known quantity, which is 4.184 joules per gram centigrade, times the change of the water, the 28.3 minus the 25.1. Plus, we got to account for the calorimeter. I have the calorimeter constant times the 28.3 minus the 25.1. Or if you want to do it step by step, which I think is easier to understand, the total Q that is absorbed by the surroundings is the Q from the water plus the Q from the calorimeter. Plug all those numbers in, add them together, and we get the total Q of the surroundings, which is 1813. Q surroundings is equal to negative Q of the system, so the Q of my system is negative 1813. Now, I also know that this negative 1813 is equal to my mass of my metal times the specific heat of my metal times the change in temperature of the metal, which is what it is right there. Guys, I can't emphasize enough. Go to the problems that are the extra problems. Work on those. Yeah, I know you're not getting graded on them, but you need to work on those because those are the ones that are directly related to what's going to happen on the exam. Okay. What are you confused about? Guys, don't be embarrassed because there's lots of this crap. I mean, literally speaking, when I was going through this stuff the first time, I was at a loss. I would have loved to have had my teacher say, what are you lost at? Is it all seeming to make sense? And I'm getting crickets here. Jasmina?
Honestly, I'm kind of.
Oh, go ahead, Gabe.
I'm kind of confused with the whole thing.
Gabe, what's
Just, like, the
confusing?
whole concept, yeah.
You can't, Gabe. You can't
I
just
don't
say.
know, it's just.
Go ahead. I'm sorry. I'll shut up.
No. I'm sorry. No. It's just. I mean, I guess just like when you read the problem and apply it and like try finding the equation.
Gabe, 3 equations.
Like,
There are 3 equations, Gabe. The water, change of the heat of the water is equal to the mass of the water times the specific heat of the water times the change in temperature of the water. Okay? So if I'm giving you a problem, okay, you got to search. Yes, I know there are a lot of numbers in here, but you got to search through it. You got to wade through this stuff. And you got to say, oh, I'm talking about the water. Where am I talking about the water? Let's see. I got the mass right here. 25.1. It was dropped into the calorimeter. When it was dropped into the calorimeter, the initial temperature was 25.1. The final temperature of the water is going to be 28.3. So now I have the change in temperature of the water and I have the mass of the water. Specific heat is a constant. You're going to have to know that, 4.184 joules per gram centigrade. Okay, so right now, Gabe, I have the water component figured out. Good?
Right.
Now, now I got to figure out the calorimeter part. Look, I got a 45.2. That's equal to the constant C. Now, the temperature, I've said on several occasions, the temperature of the calorimeter is going to be the same temperature change of the water. The water was 28.3 minus 25.1. So right now, all I have to do for the heat loss to the calorimeter is multiply 45.2 by 28.3 minus 25.1. Okay. I add those two together.
Okay.
I add those two together. That is the heat of my surroundings. That's going to be equal to negative the heat of my system. My system being the metal which lost heat. Okay, Gabe? Gabe, are you with me?
Okay.
So whatever my
Yeah.
calorimeter and water, whatever that heat was, I have to make that whole number a negative. That is going to be my heat of my system. In this case, it's the heat of the metal losing temperature. So I have that heat of the metal losing temperature is equal to the mass of the metal times the specific heat, which is what we're calculating, times the change in temperature of the metal. Now, you have to understand the final temperature of the water is also going to be the final temperature of the metal. So all I have to do, I have the Q of the surroundings. I make that number negative to get the Q of the metal. Then the Q of the metal is equal to 52.1 mass of the metal times the specific heat, which is what we're solving for, times the final temperature, the 28.3, minus the initial temperature, the 79.8. Gabe, I can't explain it any better than that. Okay? Right now, Gabe, if I were you, I would get off, once you get off of here, as soon as you can, I would go to those videos in the online outline and look through them. Maybe something they say will spark something. But it's really nothing more than plug-in formulas. Okay? Jessica. Jessica, you there?
Yes.
Jessica? Okay. How are you understanding this? Are you okay with it?
Somewhat. I like a lot of stuff that's the whole homework section. There's nothing that we went over in class that's on the homework, I feel.
In the MyLab and mastering?
Yes.
It
And
is.
I'm having a real hard time even finding that stuff in the book, like even examples. So
Jessica, it's probably that you're not looking at breaking down the equation right. Are you free after class?
yes.
Then stay after class and I'll go through it with you.
Okay, perfect. Thank you.
The trouble is, guys, I can't stay on this for the rest of the semester. You're going to have to get it. If what I'm saying isn't making sense to you, then you're going to have to go to the online outlines. You're going to have to go to the text, read through the text. But you're going to have to find some way that you're going to be able to wrap your mind around this. Or you're going to have to come up with specific questions as to why you're not understanding something. But unfortunately, I do have to get on with this. Okay, guys? Study it. Have specific questions. Email me with those specific questions, okay? I'll be happy to spend the time with you. Okay. Now, what we've been talking about right now is we've had a calorimeter that's been open to the air. Okay? It's been open to the air, and so we haven't controlled the volume, but we have controlled the pressure. We've controlled the pressure because we've let the reaction evolve in regular atmospheric pressure. Now, you can do this same reaction where instead of controlling the pressure, you control the volume. And that is something called bomb calorimetry. It's the way the food calories get calculated. Basically, you have a very rigid container. Inside of this rigid container, you have a vat of water. You're able to take the temperature of that water. Inside of this water, you have a reaction chamber. Generally speaking, you will put something in this reaction chamber and you will introduce oxygen into it. It sparks. Once the oxygen sparks, it blows up whatever's inside, which is why it's called a bomb calorimeter. It blows up what's inside. The energy what's inside of this chamber gets transferred to the water, and we're able to see the temperature. The difference between this and the constant pressure. Right now, we have a constant volume. Before, we had constant pressure. And really and truly, the only difference between the two, and it's a slight little semantic thing. When you are measuring with the bomb calorimeter, you are measuring the change of energy. You are not measuring the enthalpy. Enthalpy was done because we were at constant pressure. We can't do that in a bomb calorimeter. We are measuring the change in energy. And that's what we want to do for food articles. Same principles hold true. The Q of the calorimeter is going to be equal to the negative the Q of your reaction. In other words, Q of your surroundings is negative the Q of your system. At constant volume, this Q of reaction is going to be equal to the change in energy. So you put a known amount in the calorimeter, you determine the Q by Q is equal to mass times specific heat times the change in temperature for the water. You make that Q negative and you divide it by the moles to get the energy. If you have a 0.11 gram Brazilian nut is placed into a bomb calorimeter and combusted, the calorimeter had 95 grams of water and the temperature went from 19.5 to 26.8. What is the caloric value in kilocalories per gram? All right. Did we measure how much temperature change occurred in the Brazilian nut? Cassidy?
I'm sorry, what was the question again? I was trying to copy down the information.
Looking at the problem. Okay. Looking at the problem. Are we measuring the temperature change of the Brazilian nut?
Yes, because the water temperature changed. All the
there's the difference. We're not measuring the temperature of the nut. We're measuring the temperature of the
calorimeter or the water?
The water. So when we're doing our Q is equal to ms delta T, are we going to use the mass of the nut?
No.
We're going to use the mass of the water. We're going to try and find the Q of the water then we are going to use that Q of water, make it negative. That will be the Q of your reaction. So Cassidy, what is the mass of my water here?
95 grams.
Okay. Do you know what the specific heat is in calories? Calories per gram Celsius.
Not calories. I know joules. Just one.
1 calorie per gram centigrade. That's what a calorie is defined as. Okay. So you're going to multiply the 95 times 1 calorie per gram per Celsius. Now, what number is going to go as the temperature final, Cassidy?
26.8.
26.8 minus the 19.5. So we do that math out and we get 693.5 calories. Guys, when you're doing these problems, just wait till the end to figure out your sig figs. Generally speaking, the temperature will be the limiting factor. In this case, you've got 7.3, you got 2 sig figs. Your final answer is going to have 2 sig figs. So we did the math. We multiplied 95 by 1 by 7.3. We came up with 693.5. The Q of the nut is negative the Q of the water. So this number becomes negative 693.5. That means my 0.11 gram Brazilian nut caused this much energy. So if I'm going to figure out the heat per gram of Brazilian nut, I'm going to take the energy that I have from the total and I'm going to divide it by the 0.11 grams for the nut. I'm going to also first change it to kilocalories. Change it to kilocalories by 1 kilocalorie over 1,000 calories. This gives you 0.6935 kilocalories. Divide that by 0.11 grams. I have 6.3 kilocalories per gram. Questions? So basically, guys, this is how, if you look at the food labels, you see the calories on the food labels, this is what they're doing, really. The industry is taking a small portion of their sample. They are putting it in a bomb calorimeter. They're weighing it, putting it in a bomb calorimeter, seeing how much temperature the water changes, dividing that by the weight of what they put in there, and that's what gives them the number that they put on the side of the box. Totally different thing. We're going to go into an area that is totally different. I need to talk about something called a state function. Cassidy, do you like Florida?
Yeah.
Okay, you want to go on vacation then. You want to go from Florida to Seattle, Washington. Okay?
Okay.
So you decide you like the south route. So you're going to go Florida through a little bit of Mississippi, Louisiana, Texas, and oh, there's a whole lot of nothing there, believe me. Going through Arizona or New Mexico, stopping off at Santa Fe, wonderful country. You're going to have Southwestern food, great. Then you're going to go see the Grand Canyon, go up I-5 through the state of California, and you're going to go all the way through Oregon, and you're going to end up right there at Washington. Okay?
Okay.
Jessica, do you like
Yes.
Florida? Do you like Florida?
Yes, I love Florida.
Oh, well, you want to get out of the heat. It's July. You want to get out of here. Only what you decide to do is you decide you're going to go straight up through. You're going to go straight up through Georgia. You're going to spend a little day in Atlanta, look at a little jazz, go to the railroad trail there. going up through Chattanooga, Kentucky, sneak through. And by the way, if you're ever in Missouri, I-70, do not travel west at 5 o'clock. This is true in fact. Then you're going to go through Kansas. Why? Because it's there and you got to get through it. Going up to see Denver. Ah, I love Denver. Fantastic city. Go to a baseball game. Fantastic place there. Then you're going to go from there to Laramie, over through here, up into Nevada, and then all the way up to Seattle. Now, Cassidy and Jessica, did you travel the same route?
No.
No.
Okay. But is your latitude difference the same? In other words, did you travel your final destination and your initial destination? If you subtract
Yes.
the y-axis on that, the amount you travel north, did you travel the same amount of distance north?
No.
Yeah, you did.
Oh, wait, yeah.
Because you started here and you both ended there. You started at the same place, you both ended at the same place. So your latitude difference is the same. How about your longitude, east-west? Is that the same?
Yes.
Yes.
So it doesn't matter how you get from Tampa to Seattle, does it? Which journey you take. The latitude and longitude difference is going to be the same, no matter even if you go all the way up into Canada and dip back down. The longitude and latitude difference is going to be the same. Does that make sense to you?
Yes.
Yeah.
All right. That is called a state function. A state function is a entity that doesn't care how you get from the starting point to the end point. It only cares about the difference between the two. If I was dealing with heating water, okay, and I really have no idea of what the specific energy of each individual water is, that value is basically too complicated. But what I could do is I could tell you the difference it takes to get from boiling water to room temperature, that cooling, or I could tell you the difference going from ice cubes into room temperature water. It doesn't matter what way, how I got from the ice cubes to the water. I could have taken the ice cubes, boiled them, and then cooled them, and that would have been the same energy change as if I just took the ice cubes and just let them go to room temperature directly. Does that make sense to you guys?
Yeah.
Okay. All right. The change in energy only depends on what the initial energy is and what the final energy is. All right. Change in energy only depends on initial and final energies. Keep in mind, remember, energy was Q plus W. Q and W are not state functions. Okay, say we take a battery and we make that battery dead by making that battery run a fan the entire time. Didn't that battery have an initial energy and now it has no energy? Isn't that true? Guys?
Yes.
All right. Now, say instead of using the battery to do work, we use that battery to be shorted out. So it's not doing any work. All that it's doing is creating heat energy. Again, I started from the initial energy that battery had, only instead of doing work, this time I used it up by generating heat. My change in energy is the same, but my Q and W's are different. Which leads us into where we're going right now. It is something called Hess's Law. Now, ladies and gentlemen, be aware of this. When you are doing these type of problems in my lab and mastering, I have railed against them constantly about this, but they still do it. They assume that since you have the book, you can use the book's appendices to find the standard information you need. So when you go to solve these problems, it's going to seem like the problem does not give you enough information. But at the back of the book, there is a table which lists enthalpy values. It lists delta H, delta S, and delta G values. You are interested in the delta H values only. So it's inconvenient for us to measure the delta H of each reaction. But what we can do is, if we have a few reactions that we know of, we can use those reactions that we know to calculate what a new reaction would be. Because again, change in energy is a state function.
So on our test, then, will we be given like a table
Yes.
of values?
Yes,
Okay.
yes, you will. Bottom line for Hess's law, the enthalpy of the entire reaction, delta H reaction, is going to be the sum of the coefficient times the delta H of the individual product, plus the N, the coefficient, times the delta H of the second product, plus the coefficient times the delta H of the third product, minus the coefficient times the delta H of the first reactant, minus the delta H times the coefficient of the second reactant. It's going to be easier when we actually have some things that we are going to do. And basically, all we're dealing with is we're dealing with a state function. And what it's saying is we can go from here in one step, or we can go in multiple steps. The overall change of energy is going to be the same. Only in this case, for the two steps, we would have to add this one and this one. Is this making sense? Am I confusing anybody?
No.
So we're dealing with, because enthalpy change is a state function, we're only dealing with the initial value and the final value. So delta H, Hess's law, delta H reaction is equal to the sum of the products minus the sum of the reactants. Now, it's important to know the state of the individual compounds. Because does water as a liquid have more energy than water as a solid?
Yes.
So when you were making your water as a liquid, didn't you have to put more energy in to make that water than if you did water as a solid?
Yeah.
So you got to be careful about the states of your individual compounds. Another, write this down. This is important. The change in enthalpy of elements in their natural state is zero. By this statement, I mean delta H O2 as a gas is zero. Delta H aluminum as a solid is zero. delta H, Br as a liquid, Br2 as a liquid is 0. The elements in their natural state, as they exist, if there was nothing else acting upon them, they would be in this state. So the delta H of elements in their natural states is 0. And basically, you will have a chart like this. It's going to be organized a little bit differently. They have a strange way of organizing them. They're alphabetical and they go by the initial element. So if I'm dealing with something like dinitrogen dioxide, you have to look in the nitrogen element, go through, it's organized in terms of, I think, how many nitrogens go first, then how many oxygens. But if you look through, you'll get used to this sort of organizational system after a while. You look through and you see what that delta H is. The delta H's that are listed are for 1 atmosphere pressure, room temperature. In other words, got 1 atmosphere pressure, 25 degrees Celsius. Now let's look at a problem using Hess's law. I have N2O4 plus 4 H2s yielding N2 plus 4 H2Os. I looked up in my table. I found out the delta H of formation. That's what delta H, small little f means. Delta H of formation of N2O4 is negative 19.5 kilojoules per mole. Delta H of water is a negative 241.8 kilojoules per mole. Since nitrogen is a gas, and that's how it appears normally, its delta H is 0. Since hydrogen is a gas under standard conditions, and it's listed as a gas in the formula, its delta H is 0. So simply, in order to solve my heat of reaction, I'm going to add the sum of the products. The coefficient in front of the water was 4. I'm going to multiply the 4 times the negative 241.8 plus 1 times 0. To that number, I am going to subtract 4 times 0 plus 1 times a negative 19.5. I do that math out. I get my overall heat of reaction as a negative 947.7 kilojoules per mole. Questions, guys? I'm hearing crickets. That means either you're totally confused or you totally understand. Is there anything about this that you're not understanding, guys? Because it's going to get a little hairy in a second or two. Let's make sure you're on firm ground. Are we good?
So was the 1 times the 0 not like it's like super relevant because it turned into 0? Was that added to the 4 times the negative 20 or 241.8?
I just neglected to put it in, Cassidy, because I knew it was going to be 0.
Okay, but when you would do that, you would add it to the negative 241.8, not like just the overall equation.
If this were something like N2 is a liquid, okay?
Mm-hmm.
N2 as a liquid does have a delta H of formation. Okay, Cassidy?
Yes.
And I would have then added 1 times that delta H of formation to the 4 times negative 241.8. And that would have been my sum of my products.
Okay. Yeah, I
Right?
get it. I get it now. Because then for the other side, if we would have done it for the other side on this one, we would have added a 1 times 0 to the negative 19.5.
Correct.
Okay.
So when I'm doing that, I'm taking, because the nitrogen and the hydrogen are in their natural states, they don't contribute to the delta heat of formation. They're just
Okay.
there. Remember, Okay, Cassidy, it did take energy to make H2 and it did take energy to make N2, but we're figuring out the change of energy. Okay. When we're figuring out the change of the energy, we're subtracting it from its natural state. It hasn't moved from its natural state, has it?
No.
So its delta is 0. So the delta H of formation is 0 because it's where it started at.
Okay. Thank you.
All right. Cassidy, I have
Yes.
this new equation. Okay. I have this new equation. Remember, it's sum of products minus sum of reactants. So tell me, what are the sum of the products? You just tell me what I'm multiplying by what.
So you would multiply 2 by negative 241.8 and add that to 2 times negative 296.8.
Okay, good enough. Jasmina? Jasmina?
Hi.
Hi. All right. Cassidy has done the products for us. I want you to do the reactants for us. Remember, it's sum of products minus sum of reactants.
So it'd be 2 times negative 241.8.
No, that's a product. Isn't water a product in a
sorry.
reaction?
Yeah, sorry. Okay, so then 2 times negative 20.6 plus 3 times, or no, you don't need to do anything because it's 0,
3
right?
times 0. Okay. So
Yeah.
the way we've set up that problem, we have taken 2 times the heat of formation of water plus 2 times the heat of formation of the SO2. From that, I'm going to subtract 2 times the heat of formation of the H2S. I add all those things together and I end up with my whole total heat of reaction. Simple, guys? Simple?
Yeah.
Okay. I want you to try and do this one on your own. Be back momentarily. Gonna have to put a bell around the neck of that lady. My wife has a tendency to travel off. How we doing on this, guys? Okay, or have you buggered out too?
I'm working on it.
Okay. Notice something in the problem though. Before the previous problem, we had the state of H2O as a gas. The enthalpy is different from the enthalpy as a liquid. Have you at least set up the problem?
I finished it. I don't know if it's right, but I finished it.
I came up with 2220 kilojoules per mole.
Okay, I got negative 22 or 2221.05.
Okay, the reason. Okay,
I
I'll
was
give it
doing
to
it
you.
really fast, so I don't know if I read all
No,
of
no,
the.
I'll give it to you. I'll give it to you.
Okay.
Cassidy, I have never taken points off for somebody that gets a calculation that close.
Okay.
Jasmina, Gabe, Jessica, are we good with this? Do we kind of come up with
Yeah.
around the same answer?
Yeah, I got negative 2,219.25.
Again, a lot of it has to do with the way you round things. Okay?
Yeah, like with sig figs, I'd round it to that.
Okay. Now, there is another problem. I'm not going to go through it. All right. Okay, I'm going to skip that last slide because I'm not even sure why I put it in there. There's probably a reason. All right, now, who likes doing puzzles?
I do.
Who hates doing puzzles? Guys, this is doing nothing but doing puzzle solving. Sorry about the phone. I'll just leave it sit. This is nothing but doing puzzle solving. But you got to have some rules. I'm sorry, that is my wife. Hold on a second. I'll be right there. Boss, is it important? Okay, dear, I'm teaching. Sorry about that. Okay, if you invert the equation, this is nothing more than the rules I gave you earlier. If you flip the equation, that means if you make the products the reactants and the reactants the products, the sign of the delta H value changes. So if you have A plus B going to C is a negative 4 kilojoules per mole, then C going to A plus B is a positive 4 kilojoules per mole. If you multiply or divide the equations, you also have to multiply or divide the delta H. So if we have A plus B yields C is a negative 4 kilojoules per mole, 2A plus 2B yielding 2C is equal to a negative 8 kilojoules per mole. Now, if we have this entire reaction here, we do not know what the delta H is, but I have 3 separate reactions. That's not what I wanted. I have 3 separate reactions. I have these 3 reactions that I do know. I do know the enthalpies of each one of these reactions. What I have to do is I have to flip these reactions and or multiply them, add all of these 3 reactions up so that I end up with this. It's not as hard as I made it just seem now. Okay. This is our goal, guys. Our goal is to get this equation. That is our goal. Now, look at our first reactant and look at our 3 equations. Do any of the 3 equations have C3H8? Guys, I need you to work. Come on, I need you to quicker on the response.
The first one does.
First one does, okay? Cassidy, is it on the right side of the arrow? Is it on the correct side of the arrow?
No.
It's
Or
not. Are they both reactants?
yeah, sorry. You said right side and I thought you meant
No,
like
I
right
corrected
or
myself.
left. Yeah.
Is it on the correct side?
Yes.
Is the coefficient the same?
Yes.
So I don't have to mess with this one. Do you see that? It's the
Yeah.
only place that C3H8 appears in any one of the three. It is on the correct side of the arrow, and it has the same coefficient as my final reaction is. So I don't want to mess with this one. Does that make sense, guys?
Yes.
Okay. Now I'm going to look at my O2s. Okay. How many O2s do I have on the left side if I would add these two reactions?
5.
Is it the same as what I have?
Yeah.
Is it on the correct side of the arrow?
Yes.
So therefore, I'm not going to mess with either one of these. When I add all three of these reactions, my 3 C's are on the product side. My 3 C's over here are on the reactant side. They are going to cancel. Similarly, I have 4 H2s on my product side, 4 H2s on my reactant side. They are going to cancel. So that the only thing I'm going to have on my left side is a C3H8 plus the 5 O2s. The only thing that's going to be left on my product side are the 3 CO2s and the 4 H2Os. So if I add each one of these reactions, I'm going to end up with this. Did you all see that?
Yeah.
All right. If I add these 3 reactions, then all I am going to have to do is add the enthalpies, and I will get the enthalpy of this whole final reaction. I add all 3 of these, I get this final reaction, which matches my original reaction. I'm going to add up all 3 of my enthalpies of the reaction. That's going to end up being a negative 2,220. Did that make sense, guys? Make sense?
Yeah.
Okay, now we're going to do something that's a little bit different. Jessica. Gabe, I
Yes.
haven't forgotten about you yet. I will get you the next question.
All right.
Jessica, okay? Look at my goal reaction. This is the one I want to eventually make up. Okay, Jessica? Does carbon appear in any one of the 3 reactions below?
Yes.
Which one?
Well, carbon dioxide.
No, I want carbon, not
Oh.
carbon dioxide. Don't pay
No.
attention to carbon dioxide. I'm just asking about carbon. I'm going to try and make the reactions down here mimic what this is. So does carbon appear in any one of the 3 reactions below?
No.
No, it doesn't. What's this, Jessica?
Oh, yes.
Okay. Is it on the correct side of the arrow? What side of the
Yes.
arrow is it? Yes, it's on the correct side. They're both on the left side of the arrow. Now, is the coefficient the same?
No.
So what do I have to do to this to make it equal that?
Balance it.
Well, this is 2C. This is how many C's?
You put them together.
No. 2 C's and 1 C. What do I have to do to 1 C to get to 2 C's? Remember, I can't add, I can only multiply. What do I have to do to 1C to make 2Cs?
So then you'd multiply it by 2.
Multiply by 2. So I'm going to take this whole reaction and multiply it by 2. Okay, so if I multiply this by 2, I have to also multiply my heat of formation by 2. Got that, Jessica?
Yes.
If this is 1C plus 1 O2 yields 1 CO2, then 2 Cs plus 2 O2s yielding 2 CO2s, I got to double this as well, which is what I did. Okay. I still don't know what the final reaction is. Now, Gabe. Okay. I've got my first reaction. Good. Okay. Now, let's look at my second reactant. H2s. Do H2s appear in any one of the 3 equations?
Yes.
Which one?
Number 2.
Okay. This is 3 H2s. This is how many H2? Well, first of all, are the H's on the correct side of the arrow?
Yes.
Okay. This is 3 H2s. This is only 1. What do I have to do to this equation?
Balance it, so make it 3.
I have to multiply this by 3 because this is only 1 H2. If I multiply this whole equation by 3, I'll make 3 H2s. I do that. I had to multiply the heat of formation. Okay. Now, Jessica, did I just bother you, Jessica? I just bothered you. Jasmina. Jasmina. Okay, Jasmina. Are the C2H6s on the correct side of the arrow?
Yes.
This one is on. Is this a reactant or a product in this reaction?
A product.
Is this a reactant or a product?
A reactant.
So are they on the same side of the arrow?
Oh, no.
So if they're not on the same side of the arrow, I have to flip it. I have to flip this reaction down here. If I flip this whole reaction, I have to flip the sign of the heat of formation. So I flip it, that negative 3,119.6 becomes a positive 311.6. Okay. Now, Jessica or Jasmina, do the coefficients match?
No.
Coefficients don't match. So what do I have to do to this bottom reaction?
Divide everything by 2.
Divide everything by 2. If I divide everything by 2, I divide the heat of formation by 2 as well. Then what I do for all 3 of these reactions, I add up everything. I get 2C. 2 is actually 4 halves O2 plus 3 H2s plus another 3 halves O2 plus 2 CO2s plus 3 waters. That yields 2 CO2s plus 3 waters plus 7 halves O2 plus C2H6. Now, what I'm going to do is I'm going to subtract out what's common. Jasmina, can you see something on the left side of the arrow that's the same as something on the right side of the arrow?
3 H2O.
3 H2Os, those are going to cancel. Jessica, can you see anything on the left that's the same as something on the right?
CH, the C and H.
CH? Jessica, I see a CH here. Do I see that compound anywhere in the?
No, I was looking at the wrong one. Sorry.
Okay, you're looking at this one.
You've
You've already said the H2Os
carbon.
cancel.
The carbon dioxide.
Carbon dioxides
Yeah.
cancel. All right, Gabe, is there anything else that could possibly cancel out? Gabe, you there?
Yeah, no, I'm there. Did we say H2O?
We said H2O, we said CO2.
No, yeah, that's it. Actually, wait, no, the O2s.
The O2s. Amazingly enough,
I think
I
that's
have
it.
4 halves and 3 halves. 4 halves and 3 halves are how many O2s, Gabe? 4 halves plus
Sorry,
3 halves.
7 halves.
7 halves. Amazingly
7
enough, how
halves.
many do we have on the right side?
7 halves.
So therefore, the 7 halves cancel with those two. The CO2s cancel. The waters cancel. And if I add everything up, I'm left with the original equation. At this point, all I have to do is add up the enthalpies. That leads me to the final enthalpy of the reaction. Okay. Gabe, look at your
Yeah.
first, this is the goal. This is the goal reaction.
Okay.
Does CH4 appear in any one of the 3 other reactions?
Yes.
Okay. Which one?
The first one.
Is it on the correct side of the arrow?
No.
So what am I going to have to do with the whole reaction?
Not use it?
Nope. Nope. How the last time? Remember when we were doing this one?
Right.
Okay. Remember, my C2H6s were not on the right side. So what did we do with this reaction? Do you remember what we did with that reaction? Somebody help him, guys.
Didn't we like,
Go ahead,
Flip
Gabe. Gabe,
no, I'm not, I don't know.
somebody
You-
answered them.
Flip the reaction.
Flip the reaction, Gabe. What we're going to do is we're going to take this reaction, and what we did was we flipped it. By flipping it, I mean we made the products to reactants, the reactants to products. So when we have our new equation out here, okay, the CH4 is not on the correct side of the arrow. So we have to take this whole reaction and we have to flip it. Okay, Gabe?
Okay.
Before it
All
was
right.
this, now it is that. When we flip the reaction, we flip the heat of formation. Okay?
Okay.
So Gabe, is the coefficient the same?
Yeah.
All right. If you only have one of that
Yes.
compound, guys, in your 3 reactions below, if you only have one of that compound and you've got the same number and it's on the correct side of the arrow, don't mess with it again. It's permanent. Okay. Let's see. I'm trying to figure out. Jessica.
Yes.
Okay. Let's look at our second reactant. Okay. Does our second reactant appear in any one of the 3 equations below?
Yes.
Which one or ones?
In the second one and third one.
The second and third. Okay. At this time, we're going to have to futz with both of these possibly. Okay. And we don't know how we're going to futz with it. So because the Cl2 appears in more than one of the equations, we're going to leave it alone for the moment. And we're going to go to the products. Now, Jessica, the CCl4 appear in any one of the three equations?
Yes.
Which one?
Second one.
So is it on the correct side of the arrow?
It's on the same side as the top.
Yep, that's what I'm asking for. Is the coefficient the same?
Yes.
So are we going to mess with this one?
No.
Okay, leave that one alone. Now, let's go Cassidy. When there's only four of you, you get called a lot more frequently. Cassidy, my last product. Is it appear in any one of the three reactions?
Yes, it appears in the last one.
Okay. Is it on the correct side of the arrow?
Yes.
Is the coefficient the same?
No.
So what do I have to do to this third reaction?
Multiply it by 2.
Okay. I add up all of the reactants and all the products. Okay. Cassie, pick something that's the same on the left and right. This is my overall addition. What's the same left and right here?
Both the hydrogens.
Both the hydrogens. I'm going to cancel those out. Anything else, Cassidy?
Both of the carbons.
Both of the carbons. I subtract those out and I get CH4 plus 4Cl2 yielding CCl4 plus 4 waters or 4 HCl's. This is the same as this. At this point, all I have to do is add up the heats of reaction. Are we good, guys?
Yes.
Yeah.
All right, I have another one here. I'm not going to get a chance to do it because I want to start on the quantum mechanics. Go through. This is the last one, I believe. And actually, I didn't go through this one by one. Try to solve this problem. And I have another one here. And basically, these are just two throwaway slides at the very end. I want you to try and do those last two slides, or those last two problems. But I really have to get into, right now, I'm about 30 minutes shy of where I'm supposed to be. Are we good, guys? Questions about what we just did?
No.
All right, now we're going to get into something called quantum mechanics. How many of you like quantum mechanics in intro?
I don't remember going over it.
This is where you would have the configurations like 1s2, 2s2, 2p6, those things.
Oh, yeah, I like this stuff.
Yeah, it was simple, right?
Yeah.
Only not so much.
I feel like that's about to really change.
It was going to change drastically, guys. Okay. So, we have to realize what is happening. We're going to go through the wave nature of light, interference and diffraction. We're going to go through the particle nature of light. We are going to go through line specters and the Bohr atom. We're going to refine the wave particle duality. And then we're going to get into the quantum model with the atomic numbers, with the quantum numbers and the shapes of the orbitals. It's going to be a little more involved. There's going to be math that's involved here. There's going to be math that is going to be beyond you because it goes beyond, it goes into calculus and it goes into matrices. We're not going to get that far into it, but I want you to have a basic understanding of what is going on here. Now, at the beginning of the 20th century, science, physicists, and chemists basically thought they had this thing killed. They thought they had everything done. They thought that light was energy and that white light existed only in waves. And waves get defined by their wavelength, which is the distance between one crest and another crest, or one trough and another trough. Waves got defined by their wavelength and their amplitude, where the line of origin is to how high the wave went. That is called the amplitude. The distance from crest to crest is called the wavelength.
We can't see the PowerPoint, by the way.
Sorry, thank you. Okay. Share screen. Okay, this is the slide I was just showing. Wavelength, the distance from crest to crest or trough to trough. Amplitude, the distance from the origin to the top or bottom of the wave. Stuff you've already had, right, guys? Have you had this somewhere back, way back when?
Yeah.
In classic wave energy, or in classic wave theory, the way they thought it was in the early 20th century, energy is related to the amplitude of the wave. Keep that in mind for a second or two. Now, we can also define the wave by its speed. And basically what we do is we measure, we have a point here, and we count how many of the amplitudes pass a given point in a certain period. That is known as the frequency. For waves traveling at the same velocity, the longer the wavelength, the smaller the frequency. Because again, we're counting. We have a given spot here, we're counting the troughs. Since there's longer distance between the crests of the waves than there are here, more of these are going to pass per given time than the longer wavelength. So, longer the wavelength, smaller the frequency. Indirect relationship. In quantum mechanics, what we're going to be dealing with, the energy is going to be related to the frequency. The greater the frequency, the greater the energy. Quantum mechanics, energy related to the frequency. Classic wave theory, energy related to the amplitude. Diametrically opposed theories. So, when we're dealing with waves, if I have a long wavelength, low frequency, low energy. Short wavelength, high frequency, high energy. Basically review. All wavelengths have a wavelength, or all waves have a wavelength and an amplitude. The frequency is the number of cycles which pass a point in a second. The speed of the wave is given by its frequency multiplied by its wavelength. When we are dealing with light, electromagnetic radiation, the speed is equal to the speed of light, or 3 × 10⁸ meters per second. So if we put all of this together, we have our first important equation. The speed of light is equal to the frequency times the wavelength. All electromagnetic radiation travels at the speed of light. So if that's the case, then we have to deal with the different types of radiation that exist. Gamma rays, shortest wavelength, highest frequency. X-rays, short, not the shortest, next to the shortest, highest frequency. Then we have ultraviolet. Ultraviolet is the energy of light that burns you as a sunburn. Ultraviolet light, you can't see it. It is beyond our eyes' ability to detect. It has more energy than visible light, which is next. Then we go infrared, then microwaves, then radio frequency. You need to understand the types of electromagnetic radiation, how as you go from gamma rays to radio frequency, you are increasing the wavelength. If you're increasing the wavelength, you are decreasing the frequency, you are decreasing the energy. Let me repeat that. Going from gamma rays to radio waves in this order. We are increasing the wavelength. If we increase the wavelength, we decrease the frequency. Decreasing the frequency decreases the energy. Even when we are dealing with visible light, there are differences. Blue light has more energy than red light. And if you remember the old Roy G. Biv, red, orange, yellow, green, blue, indigo, violet.
Hey, Professor.
Yes, Gabe, bye.
I'm sorry. I need to go to class. I have another math
understand,
class.
Gabe.
All
I
right. I'm sorry.
understand.
I'll look over the recording again.
I
later on
appreciate that,
tonight.
Gabe. I appreciate that. Guys, I know I'm going over a little bit, but it's something I need to get through.
Yeah, I also have to hop off because I have a bio exam in 15 minutes. So.
Okay, Jasmine, fair enough. Guys, we're going to stop here then. Fair enough. All right. Maybe I'll increase it or start at 9 o'clock on Thursday. But I got to get you back up to speed with the other class. Okay.
All right.
Anyway, that's all we're going to go through today. All right. Cassidy, Jessica, did the stuff we went over today seem a little better than the stuff we went over last week?
Like 1,000 times better, yeah.
All right. Are you understanding the calorimetry formulas a little better?
A little bit. I honestly just think I need to just sit down and do the extra problems to really get it into my head.
I really would suggest that, Cassidy. I really. Jessica, you okay?
I guess I'll just go over the video again and stuff. I don't.
Maybe, Jessica, maybe instead of going over this video, maybe going over the video that's on online outline.
I've already looked at all those.
Okay.
Yep.
How do I compare, Jessica?
I mean, honestly, like I said, the homework is, I feel like, nothing like what you're teaching in class, and really like in the online videos, like it's, I don't know, it's really different. I'm having a hard time with the homework.
Okay, let's stop share here. Cassidy, you're welcome to stay. I promised Jessica I would stay a little longer. Okay, you're welcome to stay, Jessica or Cassidy.
All right.
All right.
I honestly stay and watch this because I haven't looked at the homework yet. So
No problem. No, you want to stay?
yeah, just to make sure I'll understand it because I haven't looked at the homework yet and I was going to do that today.
Okay. I thought it was due on Thursday.
I'm assuming so. That's when our homeworks usually due.
Well, it's usually due a week after I finish with the topic. So I might give you a little extra time.
Yeah, that would be nice.
The trouble is I'm running out of extra times, you know, because I definitely have to get through a certain amount of stuff.
Right.
And I always do this with trepidation because sometimes they cross me up. Okay, we're dealing with thermodynamics, right?
Yes.
Okay. I'm going to do this a little bit differently. Okay. Do you recall a specific question, Jessica?
All of them, honestly. I went through half of them and I had no idea what to do with all of them that I went, like the first 7.
Okay. All right. All right. All right, Jessica. All right. Part of the problem is this should be, the label of that should be kilojoules per mole. Okay?
The label of what?
I'm sorry, excuse me. Sorry. This heated reaction, the
Are you-
amount of that should be kilojoules per mole. Okay? Jessica?
Yes, I don't know what you're talking about. Are you talking about problem 1?
Are you seeing the screen? What are you seeing on the screen right
Showing
now?
what's in the homework, not actually like a problem that you're on. It's just showing like the
Okay.
different sections of it.
How about now?
Yes.
Sorry. Okay. What I was talking about is this number, the delta H of reaction, should be in kilojoules per mole. Okay?
Okay.
So you're given 3.25 kilograms of nitromethane, and you're told it completely reacts. Now, nitromethane is this compound right here. Okay, Jessica?
Yes.
Do you have, if you know the weight of nitromethane, can you
It-
tell me how many moles it is?
It was like 64.01, something around there.
Okay,
Yeah,
Carbon-
61.04 grams.
that is what the molecular weight of CH3NO2
Oh, sorry, what
is.
did you ask for?
I asked for the moles of
Oh.
nitromethane.
There's 2 moles.
Nope. They gave you the kilograms. Okay, Jessica?
Okay.
They gave you the kilograms. They gave you 3.24 kilograms. You got to multiply that by 1,000 grams per kilogram to get 3.24 times 10 to the third grams. All right, Jessica?
Okay.
Then you're multiplying that by 1 mole over 64 point, whatever the molecular weight, 04?
61.04.
Okay, so you do the 3.24 EE third divided by 61.04. This gives me 53.1 moles of nitromethane. Good, Jessica?
Did you say that you typed in the E, whatever that number is?
I put since, okay, in order to go from kilograms to grams, I multiplied it by 1,000 grams over 1 kilogram.
Yes.
So 3.24 kilograms equals 3.24 times 10 to the third grams.
Why does it times 10 to the third?
Because in order to go from kilograms to grams, I have to multiply the kilograms by 1,000 grams over 1 kilogram.
Okay.
You said that okay, like you weren't convinced.
No, because I still don't understand why you would add, why wouldn't you just do the 3.24 times 1,000? You're adding
That's
in.
what I'm doing. That's what I'm doing.
But you said you added in that 10 to the third.
Well, Jessica, when I multiply 3.24 by 1,000, I get 3,240, right?
Oh, okay.
Which is equal to 3.24 times 10 to the third.
Oh, okay.
All right. So that's the amount of grams of nitromethane I have. I then divide that by the molecular weight, which is 61.04, and I get 53.1 moles of nitromethane, correct?
Yes, when I typed that in though, I got just 3,240.
But Jessica, that's grams of nitromethane, right?
Yes, but you're saying you got 10 to the third. I don't understand where you're getting that from.
Okay, Jessica, scientific notation. If I had 5,243, changing that into scientific notation, the decimal point goes between the 5 and the 2, correct?
Yes.
So I'd have 5.243. Then I have to multiply that for scientific notation times 10 raised to an exponential power, right?
Yes.
So in order to take the 5,243, in order to make that into 5.243, I had to move my decimal place 3 places to the left, right, Jessica?
Right. I'm sorry. I understand that. I thought you were adding that in somewhere. I'm sorry.
No. All I'm doing is
I
multiplying.
understand
Okay, so I'm taking my 3,240 grams and I'm dividing it by 61.04. That gives me 53.1 moles of nitromethane, correct?
Yes.
All right, now here comes the tricky part. Now, you notice I said that this was 1418 kilojoules per mole. But
Yes.
that has to encompass also the coefficients that are out here. In order to get 1418 kilojoules, I need 2 moles of nitromethane. Because the coefficient is 2. I need 2 to make sure that the reaction goes to completion. When the reaction goes to completion, I have 1418 kilojoules. Okay?
Okay.
So in order to get the 1418 kilojoules, I need 2 moles of nitromethane. So in order to go from moles, in order to go from my 3240, my 53.1 moles of nitromethane, I have to multiply that by negative 1418 kilojoules. But in order to get this much energy, Jessica, I have to have 2 moles of nitromethane. So this negative 1418 kilojoules comes from 2 moles of nitromethane. So I multiply the 53.1 moles times a negative 1418 kilojoules per 2 moles of nitromethane. And I do that math out and I end up with 37,647 kilojoules. Are you seeing what we did here, Jessica?
I'm just doing the math right now.
Cassidy, are you seeing what's going on here?
Yes, I am.
Is it making sense to you?
Yes.
Okay.
All right. I'm gonna go because I need to take my dog on a walk because he keeps whining at me. But
Oh.
thank you.
If you put them in a box, they stop doing that.
Oh, I think
after a week.
he would just start barking at me.
And then you got to throw the box away.
Yeah. He's also a little too big for that one.
How big is he?
Like 70 pounds. He's a golden doodle labradoodle mix.
Oh, absolutely love him. I had 3 Goldens for the longest time.
Yeah, he looks like a golden retriever, but black.
Okay, I understand that. Anyway,
Yeah.
have fun walking him.
Thank you. Have a good day.
You too. Okay, Jessica, did we get an answer?
Yes, I got negative 150,534.
Okay, let's see. I got a different answer than you did. Okay.
Okay.
All right. I'm doing something for a second. Okay. All right. How many moles of nitromethane did you get from the 3,240 grams?
Okay, so I took the 3240, but you said to put it in the, I guess, the scientific notation, and then I divided it by 61.04, and I got 53.08. And then I took 53.08 and times it by 2 moles.
No. This is, I need to have 2 moles of this to get this, right? So what you're doing is you're multiplying by this number divided by 2 moles.
Okay. So
It's a conversion. Think of it as like a conversion factor. Okay. If you had 3 yards, okay, and you had 36 inches, to convert something from inches into yards, you would put the 3 yards over 36 inches, correct?
Yes.
Okay, so our conversion factor here for this equation is for negative 1,418 kilojoules, I have 2 moles. So I put the negative 1418 kilojoules, divide that by 2 moles, and multiply that by your 53.1.
Okay, so you take the negative 1418 and divide it by 2, you said, and times it by 53.08. Okay.
Remember, you got 3 sig figs here, Jessica. This number here is going to limit you to 3 sig figs.
Okay. So I got negative 37647.9. And so it would be negative 3.76 times 10 to the 4th power.
Yep.
Okay.
1 second, Jessica. Hello, this is Greg. You're probably looking for my wife, and she's probably in your lobby. Okay, thank you. Okay, Jessica.
Oh, could you go back to that that last question really fast? I had a question about it.
Okay.
So when we're doing these problems and whenever we see the delta H degree sign and the reaction equals like a negative this number, do we always know that we divide it by the first?
You divide it by the coefficient in front of the compound you're dealing with. For
Whatever
example,
they're asking for.
yes. For example, if they would say something like, how much heat is produced by the creation of 88.02 grams of carbon dioxide. Okay? The first thing you would do but for that would be you would take your 88.02, turn that into moles of carbon dioxide, which would be 44.01. That would be 2 moles of carbon dioxide. Then, since this number in front of the carbon dioxide is 2, you then put the 1418 divided by 2 because that is the coefficient in front of the CO2.
Okay.
So whatever you're doing here, you put this number over the coefficient.
Okay.
Okay?
Yes.
By the way, look through the slides. That one's in there. Okay, we have that much liquid.
I don't know, for me to go through to look at the problems like in the homework, and I always try to go back to the PowerPoint, and they just don't match up to me.
They could be better organized. I will grant you that. They don't go through sequentially like the.
I know, I'm not even talking about sequentially. I'm just saying it's hard to, I don't know. It's hard to find examples too in the textbook. I don't know. I don't think it's very, I don't know. I'm struggling with it.
I can understand that, Jessica. Okay. All right. Okay. Okay. I'm sorry, I'm looking through here. I'm trying to figure out what they're doing. Okay. Okay.
What? Come here.
So who do you have?
Oh, I have my cat Jules.
Ah,
She's like, let me show you. Can you see?
we've got a neighbor cat that looks just probably not as furry and
She's real.
skinnier.
And I have a 75-gallon saltwater a reef tank. I
Uh-huh.
grow coral and stuff, and I have a little 5-gallon freshwater, like a little planted tank. I want to get a Doberman really bad, but it's really hard to get a dog right now because of COVID and everything. Well, I mean,
It's
I guess
hard to
the
get
dog.
Well, a lot of people have wanted the companionship, so they've gone,
Yeah.
which is a good thing, actually.
Yeah, definitely. She's a perfect cat, though. I got her from a rescue like 5.5 years ago, and she's been.
Okay, I got the right answer.
Okay, awesome.
All right. I don't like this question, and everybody's getting credit on it.
Okay, awesome.
All right. Basically, what they wanted you to do was they wanted you to take the heat capacity of the colorimeter, the 52.72, the 5.72 kilojoules, and multiply that by the delta T, 38.92 minus 26.44. If you do that math out, you get a positive 71.38. Okay? That is in kilojoules. Okay? The
Okay.
heat of reaction is the opposite of the calorimeter, Q the calorimeter. So that becomes, that 71.38 becomes negative 71.38. Then all you have to do is take that negative 71.38 and divide it by the 1.554. Okay?
Okay.
All right. They skipped a step in this. They skipped a step in this, and I don't like the way they did this problem. So as a consequence, everybody's getting credit for 7.5. Okay?
Okay. Thank you.
All right. We just went over this one today. Okay, Jessica?
Mm-hmm.
We just went over this one today. All right.
Okay.
This is a direct Hess's law problem. Sum of the products minus sum of the reactants. Okay. Now,
Okay.
manganese in its solid state has a delta H of 0. Aluminum in its standard state has a delta H of 0. So you don't have to worry about the aluminum or the manganese. All you have to worry about is this one and this one. So you tell me how you're going to solve this problem.
So I take the negative 520.0 and then divide it by 3.
Nope. Hess's law, we're multiplying in this occasion. Okay.
Oh.
We have, we're saying, all right, what this is saying, Jessica, is if for every 1 mole of this that's produced, we generated 520.0 kilojoules of heat. Okay.
Okay.
But we had 3 of them. We didn't have 1, we had 3 of them. So we have to multiply what this is by 3. But there's an even bigger thing that you're missing. Hess's law says what? Do you remember what we were doing with the Hess's law?
No.
Sum of the products minus sum of the reactants. Is that
Right.
familiar now?
Yes.
So what's the heat of formation of aluminum oxide?
The negative 1675.7.
We're going to multiply that by 2.
Mm-hmm.
Then we're going to subtract from that. What's the heat of formation of the manganese 4 oxide?
Negative 1560.
So we're going to subtract our aluminum and our manganese oxide. That will give us our overall reaction. Okay?
Yes.
Okay. If something produces heat, okay? Now, you have to understand, we're talking about the surroundings. If a system produces heat, have the surroundings gained or lost heat?
I always get these problems mixed up and wrong. If a system produces heat, so it's positive, and then
No,
it's doing
if the
negative.
system, okay, if the system produces heat, you have to figure out what you're talking about. In this instance, we're not talking about the energy of the system. We're talking about the surroundings. So the system produced heat. That must have meant that the surroundings must have absorbed that heat, correct, Jessica?
Yes.
So if the surroundings absorb that heat, that means the sign of this is going to be positive for the surroundings, negative for the system. Okay, Jessica?
Okay.
Now, the system did 28 kilograms of work. Okay? If it
Yes.
did 28 kilograms of work, then you lost energy. The system did that much work, so it was negative for the system, but again, positive for the surroundings.
So it's the 92.
Nope. Remember, the surroundings gained the 120 for the heat, and it gained the 28 from the work. So that's going to be that number. Correct. Did you understand that, Jessica?
Nope, because I don't see how a negative 120
Okay.
plus a negative 28 equals a positive.
Okay. All right, Jessica, what you have to do is you have to understand whether you're talking about the system or whether you're talking about the surroundings. What happens to the system, the opposite sign happens to the surroundings. Does that make sense?
Yes.
All right. When I was going through my lectures, I was talking about all these problems related to the system. So let's look at what happens to the system. It produced heat. If it produced heat, then the system lost that heat. It produced, it made heat. So the system produced heat, the system itself lost energy. Does that make sense, Jessica?
Yes.
So according to the system, it lost 120 kilojoules of energy to the heat, correct?
Yes.
All right, the system did 28 kilojoules of work. If the system does work, that means it's expended energy to do that work. So there's also less energy in the system. So the negative 28, the 28 is negative because we're still talking about what's happening to the system. Correct?
Yes.
So according to this, the energy as it relates to the system is a negative 148 kilojoules, which rounded for sig figs makes negative 150 kilojoules, correct?
Yes.
All right, now we're going back. We want to know what's happening to the surroundings. The surroundings has a negative sign to what's happening to the system. So if the system is a negative 150, then the change of energy for the surroundings is it gained 150.
Okay. So it's just always opposite of it?
Surroundings, the change of energy for the surroundings is going to be the same in quantity, but negative the sign of what's happening to the system.
Okay.
Okay. Meat and potatoes reaction, or meat and potatoes sample. Okay. Do you see anything in this problem that says the calorimetry constant of the calorimeter? Do you see anything in that, in the problem?
No.
Good. You're not supposed to see it. What that means is when they do not give you the calorimeter constant, or they don't ask you to solve for the calorimeter constant of the calorimeter, this means we're assuming that no heat is absorbed by the calorimeter. Does that make sense to you, Jessica?
Yes.
All right. Now we have to go by the stance that Q of the system is equal to negative the Q of the surroundings. Right? Does that make sense to you now? Jessica?
See that last part again?
Q of the system is equal to negative the Q of the surroundings.
Oh, yes.
All right. Now, our surroundings are going to be what? The water or the metal? What do you put the metal in? What's the metal surrounded by?
Water.
So we're dealing with the water. Surroundings in these kind of problems are going to be the water.
Okay.
Okay. So our other formula is Q is equal to MS delta T. Right, Jessica?
Yes.
So I need to find my Q of my water so I can relate it back to the Q of the metal by taking the negative of it. That's the strategy we're going to use. All right, you tell me, what's the mass of my water? Assume 1 gram per milliliter.
It's
How much water do you have?
1.20 point milliliter.
120 milliliters, right? Normally speaking, when they give you something in volume, just assume that the density of water is 1 gram per milliliter. So if you have 120 milliliters, how many grams do you have?
0.12.
No. If you have 120 milliliters
Oh,
and the density is 1 gram per 1 milliliter, how many grams do you have?
I don't know. I'm sorry. I've only got 3 hours of sleep, and my mind is not.
This will be the last problem. I just want you to work through one of these right now. Okay. if you have 120 milliliters and the density of water is 1 gram per milliliter, then you have 120 grams of water. Okay, Jessica?
Okay.
So that's the weight of our water. Do we know the specific heat of water?
4.18.
4.18. Always use what the problem gives you. Now, do we know what the final temperature of the water is?
Yes, 21.10 degrees Celsius.
So that's the final temperature. What is the original temperature of the water?
22 degrees Celsius.
So we've set this up. We have 120 grams of the water times my specific heat, 4.18, times my final temperature, 21.10, minus my initial 22. So I do that math out. And this gives me a Q equal to 451.44. Okay? Now,
Okay.
Jessica, 120 point. How many sig figs?
3.
3. Okay. How many sig figs in a specific heat?
3.
You take 21.10 minus 22. Right?
Uh-huh.
That gives you 2 sig figs. So just keep in the back of your mind that the temperature is going to dictate how many significant figures. Crap. That's in normal. When you're doing a problem for me, that's how you're going to figure it out, the sig figs. Here, what they do is they tell you that they want 3 sig figs. Okay?
Okay.
So I do that math. I take the 120 times 4.18 times 21.10 minus 22, and I get a negative 451.44. So if the Q of my water is negative 451.44, what's the Q of my metal?
I'm not sure.
You said at the very beginning, the Q of the system is equal to negative the Q of the surroundings. And you also said the surroundings are the water and the system is going to be the metal. So if Q of the metal is equal to negative Q of the water and the Q of the water is negative 451.44, what's the Q of the metal?
Positive.
Positive 451.44. Now, that also is equal to ms delta T, but it's equal to the mass of the metal, which I believe that's what we're solving for. So mass of the metal is what we're solving for, times the specific heat of the metal, which is what?
0.452.
Okay. Times, okay, now what is the final temperature of my, what is the final temperature of my water, of my metal?
Of your metal. The final temperature is 21.10.
21.10. It's always going to be the same temperature as the water. What was the metal originally at?
22.
No. A chilled
Oh, the
steel rod at?
2 degrees.
Okay. So all right, 19.1. So I'm going to take my 451.44 divided by 19.1 divided by 0.452. All right, so the way I'm solving the final part, we started off by finding the Q of the water, correct, Jessica?
Yes.
All right, once we had the Q of the water, we made the Q of the metal negative that. It was 451.44, so it turned out to be a positive 451.44. So the 451.44 is equal to the mass of the metal, which we're trying to solve for, times the specific heat of the metal, the 0.452, times final temperature, which was 21.10, minus the initial temperature, 2.00, which is 19.10. I then take the 451.44, divide that by 0.452, divide that by 19.1, and I end up with my final answer of 52.3.
So first you time them and then you divide them?
Okay, here's the way I do it. Okay, you can,
It's kind of,
the math will work out the same, but you have to do it in this order. If you are in your calculator, the easy way to do this is to take what the number that you're starting with, hit the divided by sign and put 452. You get an answer, right, Jessica?
okay.
So you take the 451, do this in your calculator, 451.44. I want you to divide that by 0.452. You got an answer, right?
Yes.
Divide that by 19.1. And that answer is
52.3.
52.3. Okay. Now, if you don't want to do it that way, I want you to multiply 0.452 by 19.10.
8.63.
Okay. Now divide, erase your answer. Now divide 451.44 by 8.63 and tell me what your answer is.
$52.3.
Amazing, isn't it? You
Yeah.
have two ways of doing the math here. Okay. If you have like a number, say 25 is equal to 6 times 3 times x. Okay. You can either take the 25 is equal to 6 times 3, 18x, and you take the 25 divided by 18. That will give you what x is. Okay, Jessica?
Okay.
Or you can take the 25 divided by 6. All right, remember our original equation was 25 is equal to 6 times 3 times x. The first thing we can do is we can take our 25, divide that by 6. That's going to be equal to 3x. Then we do that math out. We get 4.16. Then we divide the 4.16 by 3. We get 1.39 is equal to x. If we divide the 25 by 18, you get 1.39. Okay?
Okay.
So it's the same thing. Jessica, if you're comfortable doing it the way you're doing it, taking the, in our first example, taking the 0.452 times the 19.1, and then taking that number and dividing that into 451.44, continue to do that.
Okay.
I just do it the other way because it's easier. I don't have to re-zero my calculator. It's a quicker way to do things. Okay, Jessica, I worked through 5 of these with you. Okay?
Thank you.
No, it's my pleasure. It really is my pleasure doing this, and I just have to wake up a little bit, but I may send out an invitation saying for you all to meet me a half an hour early.
I
next
can't
class.
do that. I have a class. I have a Zoom class literally
Moments.
in 15 minutes before your guys' class starts.
Okay, then I will try and stay afterwards. Do you feel a little better about this though?
Yeah, I do. But I might, if I can't get a tutoring, I have a tutoring appointment for chemistry today already, but if I can't get another one, then I'm going to attend your class later on today.
Okay. That I'm going over the same stuff. I'll probably get a little further.
Okay.
Okay, I've stopped sharing for the moment. I don't want to remove it. I want to get out of here. I want to go into the grade book, save and continue. I'm trying to eliminate. I don't like the way that one problem was set up. Course home. Okay. No, I don't want that. Why do they? Yeah, there we go. Course home. Sorry, Jessica, you can go. I'm finished. All right.
All right. Thank you very much. Have a nice day.
You have a nice day too.
All right. Bye.
Bye.